Hello, we're Team 3. I'm Riley, and I'm joined by Michael, Dingyi, Isaac, Ryan, and our team lead, Sayan. And we're very excited to share our work on improving the 3D representation of rivers in digital elevation models, or DEMs. Let's start out with some background. Topography is represented by DEM. Bathymetry is the measurement of the topography beneath the water. Ideally, a DEM could be created for the entire surface of the Earth as if it didn't have any water at all. But unfortunately, remote sensing techniques such as LiDAR cannot penetrate well enough through the water, and publicly available DEMs do not have riverbed information in them. This is an example of what a current publicly available DEM could look like. It only shows the topography outside the river, but we have no idea of the topography beneath the surface of the water. Here we can see a sample of what a DEM that includes river bathymetry would look like. In order to create this type of DEM, we need to know the location of the river using center lines, the width of the river using bank lines, and the depth of the river. Our team has created methods to determine estimations for center lines, bank lines, and water depth. The study area we're focusing on is the Upper Wabash River Basin in Indiana.
Okay, so as part of our objective was to determine the river, how wide the river is, and then in order to do that, you need to determine the river bank line. And one of the problems we are also trying to solve is that how do we do this on a very large scale? For a very small river, you can just do a digitization, but then on a larger scale, will you be able to do all those manual work? So how do we do this on a large scale? And then to do this, you have a really large DEM, and then we focus we do a pixel-based classification, and then you come out with training samples that is classifying each of these pixels into identifiable components. So you feed that into the system, and then you execute the task, and then it's going to classify the DEM into several classes. So I'm going to show you that. So on the upper right, you see the DEM, the deeper purple portion of it. It's the river, and then when you feed that into the system comes out with that 4 classifications. But on the lower portion, you are just seeing 3. And then on the far right, you can see the classified river channel. So this is the results. We just have a short snapshot, a very quick snapshot of the results. So you can see that in the lower section of the river, what the model was able to come out with a very reasonable channel of the river. But then if we go to the northern section, we couldn't get that due to some physical obstructions, and some of the river channels are inactive. And then there are some also with tree canopies. But then overall, the algorithm was able to come out with the classification based on the river channel. So we also tried several methods. Michael is going to talk about that.
Okay, so one of the other methods that we tried is using deep learning models. And then we tried the segment Zhou and the UNet model. So I'll first talk about the UNet model. For the UNet model, for you to be able to use a digital elevation model for segmentation, we need to derive some layers, some features. So we went ahead to get some DEM derived layers, such as slope, flow accumulation, geometric curvature, positive openness, and then topographic position index. But for the study area that we're working in, it's quite very large. And of course, time constraint and computational limitation, we could only derive 3 of those 5 layers. And the results are still not ready yet. But for the GeoNet segment Zhou, which is already available segmentation for geospatial data sets, which is trained with over 11 million features. We try to use that for automatic detection of river boundary. And you can see the result just using satellite imagery. You can see what that looks like. So this effort is very useful for this particular application, because online digitization of river boundary would be, time consuming, and we cannot really do that for a really large area. And of course, depth detection as well. We tried other methods, so aside just because we need to determine the depth. For us to be able to, get accurate depths, we tried satellite bathymetry using Landsat 8 and also ISAT. But the current issues with that is that the National Oceanic and Atmospheric Administration does not provide electronic charts for small rivers. So for that reason, we could not, the efforts into that could not yield very positive results. Thank you.
Okay. So the next part is what depth estimation. So for this objective of this sub-study is to estimate the maximal depth of river channels from public available data sets using statistical and machine learning models. So to do so, first, we select one open source data set, which is called HydroSwamp dataset from USGS. And then we do the feature selection. We select latitude, longitude, drainage area, stream width, stream flow, stability of the waterbed, and the materials of the waterbed. And after that, we implement 3 statistical and machine learning models, and they are ordinary linear squares from the linear regression, random forest, and the deep neural networks to predict the maximal depth. And for the evaluation metric, we use R-square and RMSE, which is commonly used in the research. And this is the result. So overall, the random forest reach the best performance, which the R-square is 0.643. Okay. And for the random forest, we can also get the feature importance. And we can see that for the stream flow, stream width, and the drainage area play an important role to estimate the water depth. So after that, we can get this trained model to estimate the water depth of our own study area, which is the Indiana's River. So in the future, maybe we can so the accuracy, the R-square is pretty fair because we only have this limit of variables. So in the future, we maybe can drive more relevant variables to enhance the accuracy of the models. Yeah, thank you.
So in terms of the geoethics, the most important issues concerning our project is how our methods and findings might be used in the future, specifically in terms of flood estimations or flood models, as improper use of findings or underestimations could have devastating effects and even lead to loss of human life or ecosystem destruction. Further details on our team's geoethics policies and guidelines can be found in our Jupyter notebooks, and more information about our sources can be found on our data card. So in conclusion, we used various geo-AI techniques to determine center lines and bank lines and found varying accuracy at different locations, with higher computational demand not always leading to higher accuracy. And we found that hybrid methodology with different techniques and data sets were more effective at different locations. In terms of the future, machine learning has potential for large-scale applications for river depth estimation and needs more extensive validation. So thank you from the River Rascals, and we're very excited about our findings, and we hope to get a chance to present them again in New York. Thank you.